Well, our paper is towards a masquerade detection system based on user task. As I said, I'm Jorge Rodríguez, and I'm coming from Technological Monterrey, but Mexico. Well, the first thing we need to ask is, what is a masquerader? Well, a masquerader is an attacker that poses as a legitimate user. We are not concerned right now how he entered the computer. I mean, he can get the credentials by leaving the user unattended his computer or by attacking the computer. And, well, it's important to detect, to develop a mechanism to timely detect masqueraders, a masquerader detection system. And the scenario we're working at is the user leaves his computer unattended for 5 minutes, and then the attacker comes and realizes some attack or actions in these 5 minutes. That's what we are working right now. This problem usually is attacked as an anomaly detection problem, where the goal is to build a classifier from the user profile. So they check the normal behavior of the user, and then with this behavior, they build a profile, and every new behavior that they detect, if it deviates from the normal behavior, then it's considered an anomaly, and it's an attack. And if it doesn't deviate, then it's considered normal. The problem with this, with a lot of anomaly detection system, is that first we have to detect true negatives for the user. That is, when the user is working his computer, say, okay, everything is normal, and do not have a high rate of false positives, because false positives are very annoying for the user. So if the system is saying, okay, you have an attack going on and there isn't any attack, then the user usually turns off his system. And the other problem is for the masqueraders to detect the attacks, because if we let pass a lot of attacks, then the system is not useful. So the way that this is done normally is they take an account for the actions, for the construction of the system. What they take in account is the actions that the user is doing. That is keyboard search, how the mouse is used, or the search behaviors. This comes from a seminal paper from Schonlo that tried to use all the commands that the user did in a session of Unix, and then with this construct the normal search models. What we are proposing right now, it's not using what the user is doing, but using where the user is doing this action. That is, we're using the file system and all the files and folders, and that is where we think we can find an approach that it's interesting to create these normal profiles. The key observation of using the where and not the what, that is the objects, is that we can do some grouping and create some abstractions. The talk right now that I'm going to show is one abstraction that we're using, that is tasks. Task basically model the actions that the user is doing. The hypothesis that a directory often holds allegedly closed related objects. That is, all the files that the user is doing for accounting or for research are generally used in the same folder. So with this, we can capture these actions, and that is what we're thinking of a task. The problem with this is that, well, we had to create a way to detect all the tasks, because in our data we don't have it tagged with the task. The data we are using right now, it's called the Windows Users and Intrusion Logs dataset. We created this log. For the time of the publication, the dataset contained 20 users, but we are extending it with 50 more users. They come from different backgrounds. They are students. We have also people that work at accounting, people that work in different parts, researchers. So it's very diverse, but right now, as I said, it has only 20 users. So the important thing about this data set is that it has attacks that are close to the real world. In other approaches to masquerader attacks detection, what they did is that they take the profile of one user, and in order to simulate the attacks, they use profiles from other users and actions from other users, and they say that that is a masquerader attack. What we did is simulated 3 attacks that are a basic attack. That is, the user leaves his computer unattended for 5 minutes, and some random passerbys come and start checking what files it has. It doesn't do any damage, but it can be considered an attack. Then the intermediate attack, the attacker starts to look for files that contain passwords or bank data or interesting files. And for the advanced one, we created a script that automates this attack, so it looks for interesting data, and it starts copying it in a USB drive. And this is done in only 5 minutes, so that's the limit of the attack. For the construction of this dataset, we take also a survey that asks the user how organized he thinks he is in his usage of his file system, so we can determine if this affects or not the detection. The problem with WUIL is that it doesn't have any tag for the tasks, and if we could ask the user to say, okay, tell us what folder contains each task, it could be a problem because it wouldn't be comparable for each user, so we did it automatically with the dep cut point, which basically says what dep in the folder structure we will consider the directory a task. In this case, if we had for this example file system a dep cut point of 4, then the task will be desktop, documents, and downloads, but the user has a lot of more tasks. So in order to compare how the task and the objects work, we are using one-class classifiers because we cannot assume that we know every type of attack that we can have. So we only have the normal user behavior. And for one-class classifiers, we take a Naïve Bayes, that is a frequentist approach. And also we take a Markov chains based classifier because it models all the temporary dependencies between how the user works between task and task. The details are in the paper, but some settings that we're using is that for the Markov chains, we're separating traces by day. That means because it needs to take in account these temporal dependencies, we're using a day separation for each trace. We take in an n-gram size of 5. That is, it retains certain memory from what object or task it passes. And an important thing is that we are currently not taking update. That is, we aren't thinking that the model is updating constantly because the file system changes every day. The user deletes or creates or accesses or moves files, but we are not taking this in account for the experiments. And for Naïve Bayes, we are also taking no update, and we're taking windows of 20 accesses to say if from 20 accesses, if it's an anomaly or not. The construction and the validation for the datasets, well, originally we parted it at 80-20 division, the 80 for the training and the 20 for the validation, but we also wanted to check how much data we needed before the performance took a hit, so we divided the datasets in 70-30, 50-50, and in order to have statistical validation, we used a cross-validation of 5 folds with 80-20. The attacks are added at the end. They are not mixed in between. So that is something we to take in account. And for us to see the results, we created the receiver operating characteristics curves. But since we didn't think that an image analysis would be very interesting or easy to do, we take in account the area under the curve associated with each receiver operating characteristic curve. This gives us a measurement of how good or how bad is a classifier. And also we take these following measurements, that is the zero false negative point, that is how much false positives we have when we have zero false negatives. The inverse, that is how much false negatives we have when we have zero false positives. And the minimum misclassification point, which takes in account the point where we have least false positives and false negatives. The results we got for Naïve Bayes, I am showing only the cross-validation results because I think that are the most interesting and also serve us for statistical validation, but all the results are in the paper. So we get for task, we get an area under the curve of 0.763 with a really, really high false positives and false negatives. With the object, we get a little less area under the curve, and with more false positives and false negatives. So we can see that at least for Naïve Bayes, that is our baseline classifier, we get a kind of decent classification, but with a lot of false negatives and false positives. When we're using Markov chains, that is the classifier that takes in account the temporal relationships, we can see the area under the curves gets better. There is a slight difference when we get better classification with objects, but we can see that the false negatives and false positives really drop down from the Naïve Bayes case. In this case, the Markov chains gives us a really better performance. So what can we say from this? Well, from the Naïve Bayes case, we can see that the difference between the two classifiers, the task-based and the object-based one, is a difference of 0.029. That is very negligible. We can really don't take it in account. And also the difference for Markov chains is not that much also. It's 0.022. So we can say that the classifier that has Markov chains has a better performance. We think that this is because we take the relationships, the temporal relationships that affect the files and how the user follows his works in the file system. So that's why we think the Markov chains is better at this point. And well, in order to do some statistical validation, we used a Wilcoxon test. We used this test because it's not parametric, and let me remind you that at this point we only have 20 users, so we couldn't use a t-test because of the normal assumption of the data. So we used a not parametric test, and with this test we concluded that the difference between the classification between Markov chains and Naïve Bayes is statistically significant, but the difference between task and objects for both classifiers, that is Markov chains based and Naïve Bayes based, they are not significant. That is, it doesn't matter if you use one or the other. Other important results that we got is the mean windows to first alarm. That is how much each classifier takes before saying, okay, we can detect an attack. Lower is better, because if a lot of time passes before we can detect an attack, then the masquerader can take the information he wants and leave the system. So we can see that the Markov chains in average have a worse mean time to mean windows to first alarm. That is, it takes a lot more time to say that there was an attack or there was an attack attempt. But as you will see in the paper, this mean average is kind of based, because for some users we have in our data sets, their results are worse. I mean, there are 3 users that are giving us problems, so that is why these problematic users give us a higher time to detection. Also, the benefits of using tasks is that first we have less number of elements to detect. That is, if we are taking in account the task that the user, we think that the user doesn't have a lot of tasks. I mean, there is nobody that does more like that. 100 activities in his computer. You do research, you do accounting, but you don't take in account that much elements. But if you take in account the objects, then you have to take every file and folder that the user uses. So one of the benefits of using tasks is that we have really less things that we need to take in account. And well, this gives us also some resiliency to change, because if the user starts adding or creating objects, then we have to update the model more often. But if these objects that he creates fall under a task, then we can say that we don't have to update that much the model, because the tasks are already taking into account the new objects or the deletion of the objects. And also, the other advantage we have by using tasks is that we have a really smaller size. You can see that it's at least 2 orders of magnitude smaller. That is, when we create all the states for the Markov chains, or what we have to take in account for the Naïve Bayes, all the states, we can see that we have a lot less states. That is better because the models have to be, the normal behavior models have to be stored in the computer. So if you take less storage and also less time to create the models, well, that gives us the benefit in the computing time and the protection times. So for the conclusions of this is, at least for WUIL, the Markov chains are better, and we don't have a really big difference between the objects used and the task used. That is good because they work the task work at least as good as the objects, and that is the abstraction we're presenting today. We aren't saying that using the objects is the only solution. I mean, it gives us good benefits, But this has to be taken in account with other masquerade detection systems. It's still an open problem, and it can be used for other abstractions. Also, well, they think that the tasks are more resilient to change, and less resources are needed. And in the further work that we are doing right now is we are taking the data from these 50 more users, and we're doing the analysis, so we will update the results. And also we're taking another abstraction that we are thinking of, that is temporal abstraction, temporal locality, spatial locality, and direction to model how the user uses his file system and other information that we could take. So that would be all. I think I went a little fast, so thank you very much.
Plenty of time for questions. Mark?
So there is one thing I didn't really understand very well. So how do you define, in your experiment, the behavior of the masquerader? Did you really did something yourself during 5 minutes which was slightly different, or did you take the behavior of another of your users that you apply to, user B to the model of user A?
Okay, no, for the experiments, we actually did some attacks in each machine of the user. So we have, for the experiments, we took like 1 month or 2 months, depending on the user. But after the time for the normal data set collection that we took, then we went to the to the user's computer, and we did attacks, the 3 attacks that I mentioned. That is the basic, that is just browsing what he has. And the intermediate attack, that is a directed attack that looks for bank accounts or all this information. And then we ran the script. So there were 3 attacks of 5 minutes. And these were the data we took for each user.
So the results are really influenced by the way you consider a masquerader will behave then?
Yeah, exactly.
And so the data set is available, so that means...
Yeah, the data set is available. We have it publicly available at this direction. All the data is anonymized, so everybody can consult it.
But I will still see the URLs and stuff like objects. What kind of objects do you have there? I mean, isn't there a privacy issue, even though can I not infer some information about your users, or at least, when they come, how much they work and stuff like that?
The objects that you can see is how he uses the file system. It's the audit logs from the Windows. So at least we don't think there is any privacy issue, because all the data is anonymized, so you cannot find any names or critical information.
Unless if they put their file name on files they create.
Mm-hmm.
Unless if they put their names on files they create, like I do when I do version 1 mark. Blah, blah, blah.
But we sanitized this data. Actually, that took a long time. So all the data is sanitized and anonymized. It doesn't contain any personal information.
Okay, thank you.
Sal?
Just clarify again, you ran a script as the masquerade attack. You didn't have real people executing a masquerade attack under a scenario?
On the data scenario, well, we say that the automatic script was like, if we had an attacker that really know what he was looking for, then he could create a script that could download all the data from the user. So it's a directed search.
I have to read the paper because I still don't understand what you tested. So.
All right, we can take it offline. I have a question. So you said that you have a 20% false positives in detection, which in many cases is a gigantic amount of false positives. But how would that reflect in the user experience? So would that, because if it's 20% false positives, but it means 1 pop-up a month or 1 alarm a month would be one thing. So I want to understand how a 20% false positive rate reflects on the experience of the user. I mean, I'm going to be, going at the user workstation 5 times a day, 5 times an hour, 5 times a minute. What is the...
Okay. First, the 20% false positives are only for the Naïve Bayes. For the Markov chains case are like 10% or 8%. So it's still big. I concur with you. That's still a lot. We didn't take in account any usage of how much, how often it will see this attack. So because it varies from user. So I don't have any data about how much repeated would
Just
be.
a rough order of magnitude, what would 10% FP be? Over here.
Oh.
Just from the data that you've worked on for all this, just roughly, is that one false positive a week, or is it once a day? Just roughly, what do you think it might be?
Probably I think it will be, for some users it would be one false positive a day, yes, but for others it would be like one false positive every 2 weeks.
Other questions? Mark?
So I'm sorry, I'm following up on this one. If you have a 10% false positive, right, it means that every 10 thing that you look at, you consider that this is a masquerader. Is that what it says, right? Yeah. So what is this thing? Is it a task, an object they touch? So does it mean that every 10 objects they touch, you will think that they touch an object they should not touch to? Or a task that they do, which I guess they do hundreds of tasks and touch hundreds of objects per day. So that would lead to dozens, if not hundreds of false alarms per day. Not one, as you just said, or maybe I misunderstood something.
Okay, yeah, I see what you're saying. That's a good question, actually. What we are giving an account every 20 objects. The thing is that for some users, the 20 objects can be a different time of lapse. I mean, some users keep 20 objects in 1 minute, and when other users can have 20 objects in 3-4 hours lapse. So it depends from the user. But we're giving it every 20 objects or every 20 tasks.
Yeah, we can continue offline. Okay, thank you.
All right, let's thank the speaker again.